No.
So where is the remote control? Again in D?
Maybe in room B.
Could someone come and bring it to me, please? This is from room H.
Yeah.
This is written here. Okay, we are now 10. Who is missing?
Why do you think so?
Okay, meantime, let's start. As he brought some chocolate, so you're welcome to the open and share it with people. So thank you, Adi. Good. Okay. Now we are all here. I don't know whether you received or whether you had time to read your emails or not. I asked Patricia to send email to everyone. I personally received it. So as I have promised, and I used to do what I promised, I checked your examination works, and would like to discuss it separately, one by one, with each person. The general message is nobody failed. This is the only information I can share. I didn't put F to any of you, so everybody passed. But of course, with different variations of, you got my message from last lecture. Although, as I said, the general situation is not extremely bad, as I have viewed it after reading a few works, but still, I'm pretty sure all of you can do much better, and all of you can proceed. Okay, so 10:30, 9:30 is okay, right? So 9:30, you know what is alphabetical order is, so who is first, who is second. I don't care. I mean, I just accept one by one person and spend not more than 5 minutes, because for most cases there is no way to discuss anything. It's clear what it is, but in some cases I look for homework, which sometimes help me to take a decision to upgrade, and sometimes convince me that I should not do this anyhow. But in any case, I communicate you that's great personally before sending it to any office, communicate it to the coordinator or sending it to Patrizia. So tomorrow is the day when we discuss. Good. So maybe before starting I take a picture because this is what I would like to put in the recording and then we start discussing science.
Sorry, I have a suggestion, like, can we go outside after the lecture and take a picture?
We can do outside too, but let me first take, if you collect yourself for this, we can do both.
3 people or 4 people.
But I hope somebody did your group picture more professionally.
No,
because I can bring my camera and do it.
Yeah,
in
outside is better.
In some professional way, but not today. This is what I usually used to keep in my office. Maybe we ask Patrizia, I mean, we definitely like to have a group picture because it's a memory of a year spent at ACTP. And maybe we will ask some lecturers to come because I'm afraid, yeah. Nice, it's okay. Let's do it once again. One more. Just to, you know. So I asked Patrizia that probably we take a picture with a few lecturers with the coordinator project, just to see all people involved in this work.
This picture does not include you.
Yes, next time. We talk about outside.
Maybe you should sit here and
no, we ask somebody else. Don't worry. Yeah. Yes, going on. This way is better. If you don't mind, I will be seated. And when it's necessary, I just call you. It's wrong. This is wrong too. Luckily, yeah. So, and in any case, so the first lecture was devoted to quantum dot. As I said, I will give Patrizia both PDF files for this. And also put it on DVD. By the way, some of you complain that not all recordings are correct. I always said it to Patrizia that sometimes I also realized that sometimes sound is not good, sometimes image is not sharp, but it seems that there are some lectures simply missing in the recording. This I don't know because I start collecting these images, but it's annoying a bit because every time I need to type my username and password and also solve a little exercise like 10 plus 4 is equal to. And since we have 20 lectures, you know, doing it 40 times plus 3 tutorials, 4 tutorials, 28 times, it's a bit boring and also consumes a lot of time. But anyway, I contact science dissemination unit and manage to copy as much as we have, but what is missing is missing. I'm sorry, it's not in my power to recover missing images. I cannot give one more lecture anyway, it will not be the same. I never give the same lecture whenever I speak, but bad luck. I hope it's on a level of fluctuations. It's not more than 1 or 2. Anyway, you have books, you have your records, you hope have some knowledge to take home, and yeah. Okay, what I'm going to show you is some brief summary of Fermi liquid theory, also showing you pictures of Fermi surfaces, which you probably didn't see. Or did I show you? I don't remember whether I did or I did not. But then we discuss the situations when the Fermi liquid theory doesn't work well, and the situation where it doesn't work at all, and we discuss reason why it is the case, and what are the theories which replace Fermi liquid theory in that situation. But before we discuss some exotic, well, it's not exotic, it's part of basic package, I would say, of many-body physics. It's just not like in Fermi liquid. But before we discuss that, we need to define what is Fermi liquid and what is not. Okay, and usually I show you this picture with iceberg, just to remind you that what I'm going to remind you and what I'm going to review is just a little piece of huge thing, most of which is behind is kind of hidden by some other stuffs, and if you like to learn more, you definitely need to go deeply inside, and that's what I'm always trying to convince you to do. Don't think that you got something which is sufficient. All time there is a room to learn new things. We are all learning during all our life, and the time we stop learning is kind of scientific death. You know, I hope you will have very long scientific life, and you'll have fun with learning and learning and learning. Okay, this is what we started our course. Fermions and bosons are different just because of symmetry. Namely, we take two identical indistinguishable particles, interchange them once, interchange them twice, and after coming to the initial state, we see that there are two possibilities to define the wave function for three-dimensional case. I mean, no topology is involved, two-dimensional cases beyond discussion. The wave function of two particles can be either symmetrical, which corresponds to phase 0 to pi, 4 pi, and even number of pi's, or it's antisymmetrical, namely the phase which appears in the wave function after first permutation is either pi or 3 pi, so odd number of pi's. In one case, when the wave function is symmetric, it's just symmetrical combination of products of single particle wave functions. We are talking about system without interaction. When the system is characterized by antisymmetric properties under permutation, then the wave function is less determinant, and therefore we are coming to Pauli principle, namely in the system of fermions, the occupation number can be either 0 or 1. So there is no possibility to have two particles with all quantum numbers identical. It's forbidden by the Pauli principle, which manifests itself on this non-interacting system as zeros of determinant when two rows or two columns are the same. Okay, so then I'm not going to talk about bosons today. At least the main part of it will not be devoted to bosons, while at the end I come to bosonization and we discuss how to make bosons out of fermions. So the Fermi distribution function at zero temperature is plotted here. The Fermi sphere volume and connection between density of particles and Fermi momentum is written here. And so I'm happy that this part of exercise, or this part of exam, was done by everybody correctly, maybe because you copied it from lectures, but I don't know. But this is also not bad, at least you understand where to copy from. Good. Now we are talking about quasi-particles, and quasi-particles basic concept. I would be very happy if you can convince me that you learn what quasi-particles are, and will be very ashamed if you tell your future teachers that you never ever heard about quasi-particles in your life. This will be very shameful for me. So, what are the quasi-particles in ideal Fermi gas? Therefore, what are the quasi-particles then in interacting system? Because the concept of quasi-particles is very important in order to treat our interacting system, Fermi system, for example, with interaction at the end of the day a system of something non-interacting, namely ideal Fermi gas. We need to map our interacting system to non-interacting one, and as soon as we can do it, we can say that the excitations of this new system, which are quasi-particles, possess these properties. On the other word, it's just diagonalizing our Hamiltonian, so we obtain our, get our quasi-particles after we diagonalize at least low energy part of the Hamiltonian, and if we can do it, we map our interacting system to a non-interacting one. So, what are the quasi-particles? Are electrons which exist above Fermi sphere. So, Fermi sphere just separates the surface which is separating occupied states and empty states, but if we can take one state inside Fermi sphere and put it outside, we have two excitations, two single particle excitations, which are electrons and hole. And of course, we have two particle excitations, which are electron-hole pairs. So, an interacting system, which is not more a gas but liquid, in analogy what we have in our common life when we come from gas phase to liquid phase, where short range order does exist, is again something very similar to the step function. However, the jump on the step is smaller than 1, and this is a reflection of the fact that we have interaction in the system. But still, after we map our interacting Fermi-liquid system to some non-interacting system, namely ideal gas quasi-particles, we have something which replaces us the connection between density of particles and Fermi momentum in the system, so, and which is known as Luttinger theorem, which says that this density consists of discrete summation over inner shell of atoms plus this Fermi volume, which comes after integration over particles inside Fermi sphere. Although it sounds very simple and very trivial, it's not trivial at all. In order to prove this connection between total number of particles and Fermi momentum in the system of interacting system, known as Luttinger theorem, one needs to proceed with quite lengthy calculations, and this proof in principle can be done, but the proof itself is beyond even advanced course of many body physics. Yeah, still, you see that the great thing about Fermi liquid is that the same relation between density and the Fermi momentum remains as it is in non-interacting system. Okay, so the excitations are particles or electrons and holes. So you see I took a parabola and then reflect this part, and in the vicinity of Fermi momentum, this is almost linear. In good approximation, it is linear, so one can characterize excitation by linear dispersion law. And this is how a two-particle continuum looks like, and I come to this point a little bit later. So what I want to show you now is how this ideal picture is corresponding to real situations. So what are the typical Fermi surfaces in real methods? We can start with sodium, with alkali metals. You see, this is the Fermi surface is pretty spherical. So the message is that alkali metal quite well described by spherical Fermi surface approximation. This is lithium. It's not very spherical, but still okay. So this is calcium. You see the Fermi surface is the holes means that it's not single connecting. So this is magnesium, but then this I think is manganese. So the Fermi surface has nothing to do with the spherical one. And when I go far into periodic table, I will have more and more exotic Fermi surfaces. For example, this is platinum. And the interesting point is whenever you take integration, all the states inside the Fermi surface and connect it with the density of electrons, the same Luttinger theorem which I just referred holds. But you don't need to think that the Fermi surfaces of real metal in many cases have anything to do with spherical shape. So shape is actually not so important for metallic properties, although the shape of Fermi surface can be responsible for interesting magnetic properties of the system. So this is, for example, how aluminum Fermi surface looks like. This is a cobalt, and just seeing comparison between aluminum and cobalt, so there is some sphere between. Aluminum is one of simple non-magnetic metals, where Fermi surface is quite isotropic in x, y, and z direction. Here you see that the Fermi surface looks like a cylinder. Moreover, there are pieces of Fermi surface which can be connected through some parallel transition, and this phenomenon is called nesting, and this is actually one of the explanations why cobalt is magnetic. So the possibility to have this parallel transition and have some congruent pieces of Fermi surface is very important for theory of itinerant magnetism in these systems. So this is how chromium Fermi surface looks like. Again, you see that this congruency and parallel transition does exist in this system. And again, this is nickel. This is like a piece of art. You know, you can put these Fermi surfaces on your wall and enjoy it in your everyday life. So, but these are all good metals well described by Fermi liquid theory. Is everything? Is it always like that? Of course not. We can take some other structures which are layered systems of two-dimensional systems, and they, of course, you saw an example with cobalt, for example, which has some kind of two-dimensional motifs in it. But the question which one may ask, if the system is quasi-two-dimensional, whether it's still Fermi liquid or not? And the answer is yes. Even in two-dimensional situation, the Landau concept of Fermi liquid holds, and there is no problem with Fermi liquid. And why? Because when we define quasi-particles in the system and define the condition when quasi-particles are well defined, from this condition we can draw the conclusion whether the concept of quasi-particles is good or bad. I wanted to show you new materials, so to say new from the point of view that materials which now come to very interesting technological application, and one of them which people start to discuss quite seriously in the last 5 years is graphene. So graphene is carbon, but single layer carbon with this hexagonal lattice structure. If one just draws the energy spectrum of this two-dimensional system, because it's single layer graphene, one sees that the Brillouin zone is also hexagonal, but the Fermi surface can be, of course, different depending on the density of electrons, but there is a special points here where the Fermi surface consists just of 2 points. So this is how graphene looks like. It attracts enormous interest just because of existence of this Fermi points, and the spectrum in the vicinity of these Fermi points is linear, resembling a relativistic situation. One should not confuse it with linear dispersion, which exists in all Fermi gases and all Fermi liquids, just in the vicinity of Fermi surface. One needs to remember that in this case, the Fermi surface has low measure. I mean, in two-dimensional situation, we expect that Fermi surface is kind of circle, but in this particular situation, special topic, Fermi surface is consisting of 2 points. So relativistic light spectrum in the vicinity of point-like Fermi surface mimics the relativistic effect existing in high-energy physics and gives a unique opportunity to test a lot of predictions of relativistic effects just in condensed matter experiment. Alternative for them is to observe these effects in neutron stars or some galaxies, which is a very difficult task. Here, this material provides, as I said, one of unique possibilities to test it in condensed matter lab, and moreover, it's related to a non-trivial topology of these materials. And on Monday, the conference starts in Adriatics, where first 2 days will be devoted to behavior of topological insulators, and most of talks first 2 days will be devoted to properties of this material and explain why this material is really unique and represents extremely interesting class of systems with very important applications. So those who are interested, please welcome to come. I think it's in Adriatica. It starts Monday at around 9, I think, and there will be key persons coming from Europe and the United States, from Santa Barbara, from Princeton, the leading expert in this field, presenting the current state of the subject. Okay, so these are, of course, not images, but result of simulation. What we discussed in our main body physics course is the two-dimensional structures, even crystalline structures, are unstable with respect to fluctuations. We discussed what fluctuations are. We estimated and behavior of fluctuation correlator taken in the same point in two-dimensional structure, and we discovered that the correlator of fluctuations is logarithmically divergent, where logarithm contains the logarithm of the size of the system. So the bigger size is the bigger fluctuations are, and I think we discussed the same thing with phonons in quasi-1 and quasi-2-dimensional system. If you calculate the correlator of displacements in quasi-2-dimensional crystal, you will get that this correlator of displacements are taken in the same point diverges, which again indicates the absence of long-range order, even in crystalline order is concerned in low-dimensional system, except zero temperature for two-dimensional system, and even for temperature equal to 0 for one-dimensional system. So how to recover, how to reconcile the resistance of these two materials? Very simple. You see that in reality, this layer of graphite, which is called graphene, is not really two-dimensional. So there are some modulation of density in third dimension, and this modulation stabilizes this quasi-two-dimensional structure. And this is how result of numerics looks like in the system, and this profile is sufficient to minimize the fluctuations and stabilize the long-range order in this kind of system. Of course, we discussed the absence of long-range order in magnetic systems. We discussed the absence of long-range order in Bose systems, and again, if one has interaction, short-range interaction in low-dimensional systems, the long-range order is eventually destroyed, and the destructive mechanism is due to fluctuation. in the system. So this is how this piece of single layer graphite or graphene looks like, and this is quite interesting technology. Level cost technology, people just take a tape and remove layer by layer. One can do it well with some experience, of course, and not in this exaggerated simple way I explained it to you. But this is low cost experiment, and the remarkable thing is that with this tape-like removing levels, you end up with a single layer structure of the crystal of a size of I don't know, up to millimeter. And this is fantastic thing. Okay, let me now remind you what we call Fermi liquid. I'm back to 3 or higher dimensional materials, let's say 3, when we have a Fermi surface, or we are discussing 2-dimensional materials with a Fermi surface, which is not point-like, but rather some shaped object. So this is a spectrum. If we reflect this piece here, we will get whole part, and this is particle part. So the excitation spectrum is linear in momentum, and the origin is at the Fermi level. So we count our energy of quasi-particles from the Fermi surface. Okay, this has already been said, and this is exercise which I did in front of you on the blackboard in order to calculate the lifetime of quasi-particles. So this damping, which describes the decay of a wave package, is inverse lifetime of quasi-particles. And in order to calculate it for the scattering when particle 1 and particle 2 scatters in new states 1' and 2', we just implement the conservation law of the momentum and conservation law for energy, and as a result we obtain one of the basic and key properties of Fermi liquid, that the inverse lifetime of quasi-particle is proportional to square of the energy momentum distance. So it's in the vicinity of Fermi surface, it's much smaller than the energy of quasi-particle, which is very important property. It tells us that if we are close enough to the Fermi surface, then the quasi-particles are better and better defined, and lifetime of quasi-particles just on the Fermi surface, where energy is 0, is equal to infinity, even in interacting systems. So, and this is in the core of the Fermi liquid. Of course, if we have finite temperature or finite frequency, we can write down the inverse lifetime of quasi-particle as temperature square or frequency square, and it actually leads to basic properties of Fermi liquid, namely that specific heat is linear function of temperature, and the resistivity is quadratic function of temperature, and susceptibility is a constant. So this is what we immediately get from this very simple calculation, which allows us to get the lifetime of quasi-particles. So this is the summary of specific heat. You see that experimentally it's usually plotted specific heat over temperature. By the way, I'm impressed that some of you got specific heat for magnetic system negative and just didn't worry about negative specific heat and so on. Maybe some of you will get negative entropies and also not be surprised, but look, when you are getting something, think reasonably about what you get, and just think whether specific heat can be negative or not, and if it is, what the physical image you have in front of negative specific heat. One needs to apply some common sense. We are not dealing with mathematical objects only. Of course, mathematics and especially arithmetic is a very important part of producing correct results, but please don't lose your common sense too. So, specific heat is linear. Specific heat divided by temperature, low temperature, saturates at some constant, and plotting it as a function of temperature square allows also to get correct contribution coming from phonons. So this is T cube, and phonons give the same contribution as magnons, and for magnons in antiferromagnet, sound by dispersion law, we calculated this T cube contribution in great details. So you see that on one hand, this linear dependence is characteristic of all Fermi liquids. On another hand, the proportionality coefficient between specific heat and temperature gives information about the density of states, which is the same time the information about mass. And one can see that after we adopt this concept of quasi-particles, namely we map interacting system to non-interacting one, what we paid as a price is that these quasi-particles are not characterized by the same mass as electrons, but characterized by effective mass instead. So the effects of interaction are encoded in two things. They are encoded in the jump of the Fermi distribution function at zero temperature. It characterizes the strength of interaction on one hand, and it's also encoded in the effective mass, which can be either bigger or smaller than 1, and in some cases accidentally it can be equal to 1, but as well as like for Fermi surfaces, I show you what are the effective mass for different systems. You see for gold it's 1.1, for silver it's again 1.1, for copper it's 1.3, but for lithium, for example, it's 2.3, which means that effects of interaction renormalize mass by some small but visible factor. We discussed it in one lecture devoted to strongly correlated systems, that effects of interaction in some systems are so big that the masses can be renormalized by a very large factor, 10, 100,000. For example, in these systems where the effective mass, the subject, or being translated, something which encodes the effect of interaction, is strongly renormalized, and this is due to strong correlation, and this strongly correlated systems called heavy Fermions. But in typical metals, you see that effects of interaction are not very strong. So, in summary, what we can say is that the basic concept of Fermi liquid theory describes the mapping between weekly in a different way. Spell check always correct us in more appropriate way. It thinks there is a correspondence between excited states in Fermi liquid and states in ideal Fermi gas. The Fermi momentum is connected to electron density exactly the same way. The theory is applicable, of course, when we discuss the degenerate Fermi gas, namely we are well below the temperature of degeneracy, which is Fermi energy. I measure, as always, I use a cycle of fluids where the Boltzmann constant is equal to 1. However, there is a difference between ideal Fermi gas and Fermi liquid. Namely, we know that quasi-particles can still interact, which leads to some interesting phenomena like superconductivity. For example, the difference is that effects of interactions are encoded in effective mass of excitations, and this effective mass is in general not equal to the bare mass of quasi-particles. And again, there is a jump at the Fermi energy in the Fermi distribution function, which is in ideal situation is equal exactly to 1, but in the system of interacting fermions, namely Fermi liquid, it is smaller than 1. Okay, so this actually is summary of Fermi liquid theory, and now I will call you that it happens that Fermi liquid theory describes very well 3- and 2-dimensional metals. However, the question is how good it is in 1-dimensional systems. So part of my talk will be devoted to examples of one-dimensional system, what kind of system we should have in mind in order to call them 1D, and I will also give you some hand-waving explanations and reasons why the Fermi liquid theory breaks down in one-dimensional system, and therefore we need to have something else. Instead, I will show you what it is. So, what are examples of one-dimensional systems? I already mentioned you the carbon nanotubes. So these carbon nanotubes can be visualized as a sheet of layer of graphene or graphite single layer, which is wrapped in a special way. Depending on the way you roll it down, you have different systems. It comes in the next slide. One can think about semiconductor nanowires like gallium arsenide, which can be grown in the direction 110, for example, such a way that it forms this kind of wires. One, of course, can think about some organic molecules which can be grown in one particular direction and are characterized by the aspect ratio such a way that the length of these molecules is much longer compared to the perpendicular size. So this is how nanotubes can be viewed as a product of graphite. Of course, no one is fabricating nanotubes using this way. They're grown up with some catalysis and they form these quasi-one-dimensional structures just in chemical way. But the point is that they really form objects which sometimes are single-wall, so kind of cylinder, sometimes are multi-wall, and these are different subjects characterized by different physics. But single-wall carbon nanotubes is almost perfect objects for one-dimensional physics. You see, I gave two examples of different way to roll this graphene up and down. So one can come to zigzag, carbon nanotube armchair, but there are some other, and the way you do it actually affects the properties of these objects. They can either be metallic and work like one-dimensional metal, or can be semiconductor, as characterized by not very good conductivity through the systems. This is a cartoon showing the spectrum of graphite. These are the cones which I showed you. So we see, this is what I said, one can get either metallic or non-metallic situation, and these are typical spectra of excitations in carbon nanotubes. There are some other examples of one-dimensional systems. I'm showing them to you just to convince you that what I'm talking is not science fiction. There are very well-defined objects which possess these properties, and these objects, attracts the experimental interest for last decades. The physics of carbon nanotube was subject of less than 10 years study, and for edge states of quantum pole, it's a bit more, probably in the last 20 years, but you see that in contrast to physics of 20th century, which was mostly devoted to properties of bulk system, physics of 21st century actually is mostly focused on low-dimensional systems. And low-dimensional systems, once again, are the systems where fluctuations are strong, correlations are strong. So instead of treating interactions as a small perturbation to an ideal, to the ideal gas, we come to a new concept which force us to treat this system as strongly interacting system from very beginning. So these are so-called H states in quantum Hall situation, which form quasi-one-dimensional motion. There are some stripes in high-temperature superconductor and some particular commensurate doping which also form quasi one-dimensional systems. And of course, there are coupled wire systems. A bit more about organics. There are many systems which possess quasi one-dimensional behavior. Among them, these Beshgard salts or DTFT systems are most studied and well understood, but there are many of them. Nice experiment was suggested and performed recently, and I will comment it in the second part of my lecture, where this circuit and these quantum wires were formed as kind of cliff state of a semiconductor on the edge. You just crack it that way, and the wire is formed just on the surface and being attached to a lead, source and drain, and subject to gate voltage, which can change the density of electrons in one-dimensional system. One comes to very nice setup which allows to measure the spectroscopy of this one-dimensional system, namely spectrum of excitations subject to magnetic and electric field, and do it in a very nice way. The reason to do it and the outcome of this experiment I show you a little bit later, and this outcome shows you the different speeds of excitations associated with charge and spin modes in the system, which is characteristic for 1D and is impossible in high dimensions. So, now I'm going to show you a few slides for the one-dimensional Fermi gas, which is normal Fermi liquid, and I show you why. And the model of one-dimensional Fermi gas, so this is parabola, is just described by this Hamiltonian, where one can see that there is scattering. So the Fermi surface in this point, one-dimensional system, consists of 2 points, here and here. All states below are filled, all states above are empty. This is one-dimensional structure. But if we produce excitations and if we consider scattering, it's, for example, possible to scatter and remove particle from here and transfer it there, the same way as we did it for spherical Fermi surface or circular Fermi surface in 3 or 2-dimensional case. And this would be a forward scattering. It's associated with a very small momentum transfer, but of course one can do opposite thing. One can take the state inside in field state and put it outside, transforming the momentum close to double Fermi momentum. And this, in the dictionary of Luttinger liquid, is called backward scattering. It's associated with a momentum transfer equal to 2 Fermi momentum. So this is how the excitation spectrum for single particle and 2 particle looks like, and you see the dramatic difference between 2 and 3-dimensional system on one hand and 1-dimensional system on the other hand, that this 2 particle spectrum, namely spectrum of actual electron hole excitation, doesn't form a continuum in 1-dimensional case. So, the Hamiltonian of this system is written here. If one linearizes the spectrum in the vicinity of 2 Fermi points, and we all remember that Fermi energies, even for 1-dimensional system, are huge with respect to room temperatures. So if we are interested in low energy physics, we can linearize our dispersion relation. So the model with linearized spectrum subject to this Hamiltonian is known as Tomonaga-Luttinger. So the basic cartoon is here. So instead of having parabola, we have 2 lines, and this is like for Dirac fermions, like in a relativistic case. So everything is relativistic everywhere, and the Fermi energy is just placed here. But the big achievement and the big consequence of this simplification compared to parabolic dispersion law is that this model is exactly solvable in 1-dimensional cases. So the suggestion came in the middle of 20th century. This Luttinger model was introduced in early 50s, but the big progress occurred just in the middle of 70s, where people realized that there is some very powerful method which allows to solve this model exactly. And another achievement occurred just a few years ago when people understood how to treat the curvature. So how to treat the difference between linear and parabolic spectrum. It's not necessarily parabolic. If one has tight binding, it's cosine. So it's parabolic only in the vicinity of bottom of conduction band. So the big achievement of 21st century is related to understanding of curvature effects and physical consequences of and corrections which appear due to nonlinearity in the spectrum of excitations. So, as I said, the breakthrough in the 70s was related with very simple, by the way, understanding. And the understanding comes when we notice that the interaction can be easily written as a density. So rho is a density operator, and one sees that, as usual, as in any dimension, the interaction is quadratic with respect to density. But it also happens that the kinetic energy term can be written down as a quadratic function of density operators too. So in some sense, and this is highly non-trivial thing, and this is due to one-dimensionality of the problem. How did it happen? One can calculate this commutator, identify the constant, and then write down this Hamiltonian. And the procedure actually says that we start with some fermionic Hamiltonian. This guy contains 4 creation and annihilation operators. But being a 4-particle term in fermionic language, it's quadratic in the language of density, and density is bosonic operator. Being able to write down the kinetic energy as a combination of bosonic operator, one comes to a very remarkable point. Namely, in one-dimensional fermionic language is not appropriate one. I'll tell you why on the next slide. But instead, bosonic language is appropriate one. So the Hamiltonian of strongly interacting system, not necessarily weakly interacting, can nevertheless be mapped not to non-interacting Fermi system, as it is in 2- and 3-dimensional case, but to non-interacting boson system. And this procedure known as Bosonization, actually was one of the greatest achievements of the last quarter of the previous century. So, and the procedure got the name of Bosonization. Why? If we write down our Hamiltonian in terms of bosonic operators and take into account both forward and backward scattering, we can then easily diagonalize the Hamiltonian using the same Bogoliubov transformation which we used to use when we diagonalize our magnetic Hamiltonian for antiferromagnets, and we diagonalize our Bose gas. And not surprisingly, like in Bose gas, the excitations of in this Luttinger liquid, namely bosonic excitations, are phonons, which are characterized by linear dispersion formation. So it is sound, and the excitations are acoustical phonons. Yeah. But then the question is, well, we calculated, we diagonalized our Hamiltonian using a different language of quasi-particles, because we started with interacting fermionic system, end up with non-interacting bosonic system. What happens if we want to recalculate the fermionic properties? For example, we want to calculate fermionic spectral functions or fermionic correlation functions. It can be done by refermionization, by coming back to fermionic degrees of freedom. And one of the remarkable predictions of this Bosonization theory, that when we do it for interacting system, we obtain something which is called spin charge separation. Namely, in one-dimensional system, the velocity of propagation of charge excitations and velocity of propagation of spin excitations are different. So these are experimental plots of the experiment with the Cliff states, which I just showed you, and one can see that in fact the charge velocity, the spin velocity, which corresponds to just Fermi velocity in the system, and charge velocity are different. The charge velocity actually is bigger compared to spin velocity, and therefore one can really see kind of separation of spin and charge objects, which is a remarkable property of one-dimensional systems. So the prediction of this Luttinger model, which had been formulated in the late 70s, had been verified in 2004-2005, and this is a remarkable experiment which proves that in fact spin and charge excitations are separate. So this is the messages to take home. Yeah, I don't want to go to quantum phase transition. And the last thing which I would like to comment, why it happens so that fermionic excitations, that the fermions do not represent a proper language for one-dimensional systems. The same way as we did for two- and three-dimensional systems, we need to investigate the lifetime of quasi-particles. And if we do it correctly for one-dimensional systems, it appears that the lifetime of quasi-particles is no more quadratic with respect to the deviation of momentum from the Fermi points, but linear. Namely, the lifetime of quasi-particle, the inverse lifetime of quasi-particle, is then comparable with the energy of quasi-particles, which means that the quasi-particles are badly defined everywhere, including very vicinity to the Fermi series. And this is why the fermionic language is not good language. So this is why one needs to proceed with bosonic language, and bosonic quasi-particles are very nice and very well defined, and the bosonic language then represents the true quasi-particle language for this system. There are many other interesting things associated with physics of one-dimensional system. I just mentioned you the very top part of the iceberg, which I showed you at the very beginning of this lecture. And the reason to give these two last lectures was to show you some interesting physics which people developed for last year, show you the new materials which people used to investigate, and some of them are called functional nanostructures, and some of them have a lot of technological application even now, and maybe we'll have more in the future, and tell you that physics, theoretical physics in particular, is not something which is frozen. You don't need to have impression that all problems are solved. It's the other way around. It's a lot of new interesting problems which appeared recently, which demand a new solution, a new approach, and new methods, analytical and numerical methods, in order to attack this problem. And there are many unresolved questions to be addressed and to be understood, and this is why it's so interesting to work in this field. And the general direction, as I said, for physics of 21st century, at least the physics I'm interested in the field of my expertise, is a physics of low-dimensional system, physics system out of equilibrium, and physics of strongly conducting systems. Okay, that's all. I think I fulfilled all my promises which I gave to you. If you have any questions, please ask me. If not, we meet with all of you tomorrow and discuss the outcome of your examination. Okay, if there are no questions, then I thank you for attending this course. I really hope that you learned